All right. Welcome, everyone. Today we have Ishan, who is visiting us from Sony AI. Ishan and I met maybe two years ago or so, but I've been, a huge fan of his work. He completed his PhD from UT Austin. Really exciting work on distribution matching, goal conditioned RL, sim to real. Basically, all the cool things that we're working on now, Ishan did 5 years ago. And so it's really exciting to have him here today because he gets things to both work and be principled, and so I'm excited to hear about Sony AI and his work.
Yeah,
Take it away.
awesome. Thanks, Abhishek. So unfortunately, I'm not talking a lot about what I'm working on right now. I'll focus a little bit more on this project that started quite actually during a little bit before the pandemic, and then they started getting it actually working during the pandemic, which was like outracing champion Gran Turismo drivers using reinforcement learning. And it led to a Nature paper, and then now we've been working on getting these like RL agents into deployment into games. So it's sort of like I'm planning to go through this like whole gamut of like research, trying to get like superhuman behavior like you have to do in RL now, and then actually get like interacting with a game studio to get things into the game in deployment. So I think it will be like an interesting study. Before I go into that, I don't know how much you all know about Sony AI. It actually got established in like April 2020, officially, I guess. Like it did already started before that, and there are a few different branches in there. So like there's a AI ethics group, gastronomy, imaging and sensing, and then like gaming, which is the group that I'm part of. We're all remote in North America, but like there are offices in Tokyo and stuff, which I hope to visit soon. And yeah, so the thing that I want to talk about today is this kind of like project that we did, training RL agents to drive not just really fast, but also tactically and strategically, so that they could race against a team of human players in this game and beat them at the game. And what this game is, it's a Gran Turismo, it's a PlayStation game, and actually the studio doesn't like it when I say it's a game. They call it like the real driving simulator, because they spend a lot of time and effort trying to get the dynamics of the game really right. So they like and the physics and everything, and they spend like a lot of time going over every inch of every track that they add in to make sure that every crack that is on the track is there and like actually affects how you drive. And I was like, yeah, this sure, whatever. But then I saw this like footage from one of the Sony people driving with a car that was spec'd out the same physically and in the game, and he's driving on the same track. And if it wasn't for that, like the rear view mirror, I wouldn't have been able to tell which was the real track and which was the game. And in fact, he got it to, I think, within like a 0.1 second in like both. So it's like a very high fidelity simulator. And it's also used in the virtual Olympics for the racing system. Like that's what they use for the motorsport. And so we actually faced off against like the elite human players twice. Once was in July of 2021, and the second was in October of 2021. The first time the humans beat them. The first time Sophy was taken in for this competition. It was superhuman in terms of like how well it could lap these tracks, but ultimately the team play sort of like affected it, and they weren't able to win. And then again, when we went in October, we were then able to defeat all the humans. So I'll like go through some of the process. The actual event was in these like 3 tracks: Dragon Trail, Maggiore, and Sarth. Sarth is this like pretty famous track where they have like a 24-hour race, Le Mans, and So for this particular event, 3 tracks, 3 specific cars, trained with individual networks for each cars. And then we'll talk about like the generalization bits later. Yeah.
Is it a multi-car setting with passing and everything?
Yes, there's like, so when we played against them, it's like 4 cars controlled by the agent, 4 cars controlled by humans, and each car is controlled independently by a separate agent. So it's not a single policy running all 4. Yeah.
Another quick question.
Yeah.
Does anything about the tracks change from time to time, or are the tracks pretty consistent?
You mean like across deployments or during the
Or
race?
like between training and deployment, or across deployments?
Yeah, so for this event there wasn't, but now there is. Like they keep updating the game, and they also like update the physics regularly if there's like new tracks that come in, or for the same tracks, like they also have like different weather conditions. So like last year I think they introduced like a snow track for the first time, and it definitely affects how you race in those cases. There was one deployment where I think something messed up in the physics, and then the car started to fly, but they rolled that back pretty quickly. Cool. So this is an interesting problem with these like 3 big challenges. The first bit is like the actual control problem. You're learning to drive a car, so it's like a hard control problem with like a high fidelity simulator. So you need to be able to control it really closely. The second bit is the strategic decision making and the long term decision making. What line do you take when you're driving? How do you overtake? When is the right time to overtake? Because ultimately you want to win the race, and you also have these like other effects of the physics and dynamics that can help you. So you can have sort of like, if you're driving behind a car, you get slipstream effects, so you can like actually gain speed. And if you're going out ahead, then you're getting like the full wind resistance. So when to overtake, how to overtake, all of these are really interesting questions. And when you want to play defensive and how you want to block. And then the last bit is there's a high level of sportsmanship that is expected from drivers, especially when you're competing. Like it's kind of like you're playing, you're in like a Formula 1 or something like that. You can't just go and like crash into other players and like throw them out. You immediately get penalized for that in official races in that they have for the GT World Cup and things like that. So these are like 3 big challenges that we had to solve. It was we thought it would be pretty straightforward, that like the control bits would be pretty straightforward, like figure out the state space, figure out the action space and the rewards, and then just go. But as I'll get into, there are challenges there as well. So we, as I already said, like we trained Sophy with reinforcement learning. I'm sure most people are familiar here, but basically we have an AI agent that takes in the state of the environment, and we sort of like extract the state in some particular ways. We give it some reward, and then the agent has to take some actions that then affect the environment, and then we go in this loop. So what's the state that we provide the agent in this case? We didn't give it the image like how humans play. We instead, because we have access to the game, we were able to extract more fine-grained information, like the velocity, the acceleration, the force on the wheels, the progress along the track, how much the tires are slipping, things like that. So yeah, that's a lot of it. And then we also gave it some information with respect to the other cars that I'll get into later. And if anybody has questions or something, like, please interrupt me. The action space was pretty straightforward in this case. It's like acceleration and braking, so plus 1, minus 1 for acceleration and braking, and then steering between -1 and +1. So 2 continuous dimensions. Yeah.
Do the agents have access to like the optimal racing lines for particular courses, or that's?
No.
Okay.
Like we could have given that in there because the information is in the game,
Yeah.
but we found it to not actually be that helpful because the agent, like in a lot of reinforcement learning situations, you see that like they do something unintuitive and find a more optimal route. So yeah. Yeah.
For their control inputs, was there any like physical limitations of like in a real car you probably couldn't go from like -1 brake to +1 accelerated? Like
Yeah. So the policy was putting out the difference in the steering rather than the actual like exact values, and we also gave it some restrictions so that it couldn't like just output +1 to -1. I forget the exact threshold that we had put in there, but we spoke with the studio to make sure that we were not doing, not giving it any values that it was capable of that were beyond human movements. Yeah. And also, it's like if you do like dither like that a lot, in fact, like driving at high speeds, you'll like go off track and things like that. So in fact, like Sophy on its own, even without those restrictions, can learn to not change its angle too much. Yeah, and then the last bit is the reward. So there were some like basic components like progress along the track, penalty if you go off track, and penalties for hitting the wall and the tire slipping and things like that. But the interesting bits in the reward design were for sportsmanship. How do you design the reward so that the agent acts sportsmanly but doesn't reduce its aggressive? Like it has to be like trying to win, but also like not be a bad player. And so like there were like multiple different types of collisions that were decided upon with like working with the domain, like the studio, and then obviously like the actual parameters, like the weights for these rewards were decided on with a hyperparameter search. Yeah.
So, is the purpose to win, or is the purpose to create a good gaming experience? Because it might be a different thing.
Yes. So the initial purpose was to win, to show that we could, like we can go superhuman, and then subsequently when we want it in the game, we want it to be enjoyable and like not even superhuman. Like you want it to be like reactive and enjoyable, and not necessarily like a challenge for whoever is playing.
Because it might also be that that reward needs to be non-stationary, right?
Yeah.
As your
Yep.
skills change. Is that something that you guys have already done, or?
Yes, there's some bit of it. A lot of it is not, surprisingly, a lot of it is not just tweaking the reward, but tweaking other bits, like what cars you're playing with, the handicap, not exactly the handicap, like how many Sophy agents you're playing with, because they sort of race against all the other cars as if they're like they're trying to just win, and so how many other agents you play with is also important, and like other bits. Yeah.
You said you have a tire slip penalty. That's for like going over the limit of grip.
Or like if the car starts drifting and things like that.
So I was wondering, do you calculate? Like, does your model calculate expected grip limit and try to drive close to that or anything like that?
So because it's like completely model free, like I'll get to in a bit, it's not explicitly looking ahead to see like, oh, what will my tire slip will be if I'm getting at this turn at this speed. But the value function and things like that implicitly sort of encode that, and so the policy learns to compensate for those bits. All big RL endeavors need big computations, so we ended up coming up with this like training infrastructure with Sony Interactive. They set up like, I think, I'm trying to remember, 200 PlayStations on like in a data center that we could like run our game on. So and each agent was actually going and playing the game in real time on each of these PlayStations, which we then collected the data from and then trained using an off-policy training algorithm, QRSAC. Which was like this was the algorithmic contribution over here. So like we combined distributional reinforcement learning with quantile regression and soft actor critic into this like method QR SAC. And it was actually really interesting because like adding the distributional critic ended up taking the agent from being like regular fast human to a superhuman stage. So we're like the hypothesis is that it helped the agent sort of like understand all the distribution of like possible outcomes and then train the policy based on that. I'm Is anybody unfamiliar with SAC or something like that? I can go into details, but like it's basically like a combination of QR, quantile regression, and SAC. And then we also had n-step returns. Yeah.
The min,
Yeah.
is it on, there's queues or distributions, right? So
Wait.
queues here are distributions?
Yes.
over-
Yes.
And so when you say take a min over distribution, what does that mean?
The min over the expectation.
Or, because I'm guessing you would do like
So there's two versions of this. There's one where you look at each of the quantiles, pick the min for each quantile, or you take the min for the expectation. The min for each quantile makes it more conservative.
Yeah.
We've done the min for the expectation instead. So it's not as conservative, but still helps.
So the M there is quantile buckets?
No, so the M is like basically we have two critic networks.
Oh, that's great.
And then you just take the min of the value over here so that for the target that you're coming up with for for your value update, and just taking the min over there just gives you slightly more conservative Q value to update to.
Are they like running in like a delayed setting, or are they like simultaneous?
They're simultaneous. Ideally, you want to be doing something statistically better, but this ends up working. Like you can also end up doing like an M of like much more. There's like if you want an even better version of it.
So
But
these are like
two heads.
kind of hyperparameters is like how you set up your critics and how you set up the quantiles, like the
Yeah.
discretization. of
Yeah. The quantiles, yeah.
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 Did you try using more than two like critics at all, or just two words?
Just two worked. I think we tried sometime later as like an experiment for like more, but it doesn't add too much value. And just like, so the other issue is like these networks have to run on the PlayStation, and at that time it was the PlayStation 4. So we needed to be like make sure that things can actually run in real time on these on these machines. Yeah, and then we used n-step returns, ended up helping quite a bit. For the July race, we used an N of 5. For the October race, we used an N of 7. Beyond that, it wasn't very helpful because it was taking too long to like in terms of computation. So as you can see, like just with like 3 to 5 steps, it ends up getting like quite a bit of improvement over there. And then the other bit was like SEC versus QR SAC. We get about half a second, which like helps quite a bit in when you're going up against the best players.
So when you go n-step returns,
Yeah.
you're becoming on policy.
Kind of on policy. So
there's this retry stuff and like to fix it, right?
yeah, so we first tried just like basic n steps, which is like on policy for 5 or 7 or whatever steps, and then you do the off policy bootstrap, and that worked. So you're like, okay, fine, let's not break it if it's working. But you're right that like you ideally want to do correction for it.
Didn't seem to need it.
Didn't seem to need it. Yeah. Yes. Yeah, and then this is like some details about the training itself. I'll go past this. The only thing I wanted to point out is like it was a fully connected network, which like seems weird at this point. But because it was on a PlayStation and we had to run in real time, we wanted to keep it as simple as possible. And so the network that ended up working was 4 hidden layers to 2048 ReLU nodes per layer. And the other surprising bit for me was that large batch sizes were what was required, like smaller batch sizes didn't end up helping quite a bit. And different learning rates for the critic and policy. Cool. Yeah, so these were the training bits. Now I'll start going through like what actually happened, like once we trained. So this is like just the time trial. So like comparing the time it takes for Sophy to lap. I think this is Maggiore, yeah, Maggiore, compared to like humans. The first graph over here is a histogram of the time it takes for humans to do a lap on this track. I forget the website where they collected this data, but and then the yellow lines over here is how Sophy progresses over training. So within about an hour, it's already getting close. Within a day, it's getting close to like the best human players. And at the end of training, which was I think 12 days, this bottom graph shows the distribution of GT Sophy's training of the lap time on this same track and how it compares to the top 5 players. And this is the track where the human times were the closest to GT Sophy. So for the other tracks, you can't even make this graph.
And this graph is for like single car time trial.
Single car, yeah. So it's just like showing that, yeah, we can drive at a superhuman pace, not that you can actually win the race itself. Yeah.
Can you go back to that graph real quick? Is like, what's the like x-axis?
The x-axis is the time it takes for one lap, and we basically clipped it so that you're not staring at
Oh,
it.
but it's like a difference of like point like one, like a huge amount in like.
Apparently, like I'm not good enough to get anywhere close to this, but but it at that stage it is. When you basically are at this like end of this peak, right? Like really minor seconds, fractions of a second matter a lot.
Is it like competitive like sprinting or whatever, where like fractions of seconds are like huge?
Yeah. I guess it's similar to like, I don't know if you've seen a Formula One race, like when they have like qualifying, you just have to like go fast, and whoever goes the fastest gets the first position. And over there you have like hundreds of a second or like even less that separate the cars, like the top 20 drivers. So it's like similar, I guess. Yeah.
You said there's like in the final thing, there's like 4 humans and 4.
Yeah.
Yeah. So is there like collaboration between the 4 agents? Like is it a multi-agent thing, or is each agent like?
We didn't explicitly train them to act as a team, but they're trying to maximize their points. They're trying to win, and so they're not teaming up to make sure that the humans lose. I guess that's like, yeah.
So during training, what controls the other vehicles?
So I'll get to that. There's like, we can either train against built-in AI or we can train against other policies, kind of like self-play. But there are issues that crop up when you just do self-play. And an example of like what a train policy looks like and why it's actually superhuman. So if you start looking at it, like the car goes really close to the walls and to the edge of the track. Something that I think would be really difficult for like a human to, unless you're a professional player. It's like very crazy. I think there's a video online of like, I think we got Hamilton to come in and also play, and like we compared how Sophy does, and like Hamilton drives like really nice and Sophy is like all over the place, but it was like almost the same speeds. So it's like interesting. The other bit, yeah, so this is a comparison to sort of show where Sophy ends up being better than humans. So the track over here is highlighted with like the same color as over here to show like these are the sections where Sophy actually gains on the human. So this graph is actually the difference between how far a human is behind Sophy, and every time you see a dip, this is where Sophy gains substantial times, and a lot of those are in these like chicanes. So chicane is like a back and forth on a straight track, so where you have to like sort of do some maneuvering, and most of these places is where the human tends to brake more or take a little bit more time to start accelerating again, and that's where like Sophy basically doesn't slow down much and gains more speed.
You don't have the same precision,
I think
so
it's really, let me see if I
it
can.
gets way more difficult to do
Actually,
the
so
same thing.
there's a ghost of
and
a
they
car
compare, like,
that you'll
very,
see
very
somewhere
quickly.
up ahead, and the human Igor is trying to catch up to that car, and he's just like, the turns are really where Sophy shines.
Man, that's fast. That's really fast. Like I really want to watch the onboard as well to see how like they throttle and braking trace,
So this,
steering
yeah.
trace as well.
One thing that this makes me think is that there's an element of risk aversion that humans have.
Yeah,
Like,
maybe.
I don't want to crash into the wall, because I die.
Yeah, but
And
also, yeah.
Does that, if you did a risk averse objective here, would it give you similar behavior too?
I mean, there is a risk averse objective because we are telling Sophy during training to not crash, to not go off track even, and the fast. Like we, in fact, the off track penalty is higher. I think it's a squared penalty for the speed at which Sophy goes off track.
And
So
let's say you did like CDF distributions of returns
Yeah.
with C-bar or something.
Yeah, you
like,
could.
do you think that would change the behavior to be more human-like?
I'm not sure. I think it's already pretty good, and in fact, like a lot of like the timidness comes from when there are other players. Sophy stays on track pretty well throughout. Like once it's trained, it stays on track really well. Maybe if we injected some sort of like noise into the actions, maybe then it would be more like try and be more robust and stay inside. We've done some of those studies for some of these things that you're talking about, like try and behave like a rookie would play rather than a professional. Yeah.
Is there any analysis of like the, let's say, slight input delay that might accumulate for those like strong braking acceleration moments that you kind of see the AI getting an advantage over the human? Like
Maybe,
maybe
yeah.
you could take like the humans, let's say, trajectories demonstrated, and then like remove any delay in the actuators, and then see if you get like a more similar overall.
So there isn't a lot of delay in the actual, like you're saying when the humans delay in like
Yeah, I
actually
guess.
pressing,
Are they driving with pedals or?
Yeah. And for Sophy, there's a I think we added a little bit of delay, plus there's an inference delay for the network, because it's like even though it's a fully connected network, it's still slow on the PlayStation, and there's a network delay. So like Sophy computes the action and then it's sent over a network to the thing. So there's like it doesn't add up to the same amount, but it's like in the ballpark.
Got it. Yeah. I'm just curious because I know there's a reaction time associated.
Yeah.
Just related to what you said, you said you tried adding a little bit noise to the agent's actions.
Yeah.
What did you find when you tried to add the action or observation noise? Was it robust?
Yeah, it learns to be robust. So this is not part of the actual Nature paper. We did this study afterwards, trying to get a more human-like policy. It doesn't actually like it. The agent becomes a little more robust, but it doesn't actually like slow the agent down or anything like that too much. So it's like maybe not going as close to the wall anymore, but it's still extremely fast. And now the other bit, which was like, how do you represent opponents when you're not doing a time trial, when you're actually in the race? So we just had a forward, like a queue in front and a queue in the back to represent opponents. We gave the other agents relative position, velocity, and acceleration to Sophy, and then the reward when you're playing with other to encourage Sophy to pass was basically like when you get close to other agents, you get more of a reward, or when after you overtake, when you're pulling away from agents, you get a positive reward, and then the negative for the opposite, like if another agent is getting close to you or overtaking you. Yeah.
Are any of these rewards non-Markovian?
No.
They're all Markovian.
They're all Markovian, yeah.
Well, like, I guess pulling over.
So it's like the current state, next state, the difference between the positions between those, yeah.
And if you were to do non-Markovian rewards, like for instance for style or how would you do that? Because SAC will like totally break, right?
Yeah, you could like, I mean, you can introduce, there's two ways you can deal with it. One is you can come up with the state features, you accumulate the state features and then like provide it to the agent so it becomes Markovian, or you can add like an LSTM or something to, so that it can figure out.
But that's not something that has happened here because you don't need it, I guess. So.
Yeah, so we mostly do it on this, we do the state modification route because it's easier and you don't have to train the train the LSTM, which can make things wonky again. Yeah. Yeah, and then the other interesting bit over here is like how do you balance etiquette? So if an agent is just trained against built-in AI, it becomes really aggressive. So it's like starts pushing the other agents off, and it so that's like a very aggressive agent. Like Sophy got penalized for that in the July race. But then if you train against an aggressive agent, if you do self-play, the agent becomes really timid. And this is an example where Yamanaka came close to Sophy and got side by side, and then Sophy backed off. It didn't even try to fight for that position. And what ended up happening, you'll see it soon. So Sophy breaks over here and lets the other player go ahead because it's been trained against aggressive opponents. So it's like risk averse in this case, and so we had to be careful in like figuring out what's the right mix of players, and I'll get to that in a bit. How we picked those exactly. The other interesting bit was like there are different skills that an agent needs to learn. So overtaking in a slipstream, how to drive in a chicane, which was like one of these like weird turns over here, playing with different number of opponents, things like that. So one of the interesting things that came out of the effort was this idea of having a lot of these different scenarios that the agent trains on, storing them in different replay buffers and like sampling from them with different proportions in a way that you don't forget the skills that you want to learn. Yeah, so this is an example of like the number of samples that we obtain for different skills. So like slipstream or like the chicane over here, and then how we construct the mini batch from this replay buffer. We did a bunch of more like analysis after the fact of like why this exactly helped, and this is like one of the follow-up papers that came out of this effort. It's called event table. So each of these events that you're training for, you put the data for that event into different replay buffers and then sample from it separately. So it's sort of like explicitly modifying the training distribution. And if you have some domain knowledge for what you want that training distribution to be, you can use this idea. And then so once the agent trains with some of these techniques, it can learn how to learn some of these like interesting things. Like this is slipstream crossover, so it like uses the slipstream to get really close to the other player and then uses that to overtake. And there's an ablation over here, but we can maybe get back to that later.
No PID opponent.
So yeah, one of the ways the agent was trained was with another agent that was just a PID controller, and yeah, on the optimal line. So we gave it a variety of lines. So one was just like staying to the left, staying to the right, staying in the center. So it was just like, oh, you should be able to deal with agents like this. And if you don't have that, it's just like less diversity to train with, and then there's some like brittleness over there. Yeah, so the opponent population. So if you train with just the built-in agent, you end up with like a GT Sophy that is extremely confident and very aggressive, like we saw in the first example earlier. If you train against, if you do just like self-play, so the agent learns to become timid and it becomes overly cautious, so it like it ends up not scoring so well. And so what ended up happening was we did a sort of like population based opponent sampling. There was a bit of like automation in this process, but a lot of it was also like some of these people who knew what to look for went in and picked policies that knew what they were doing, or you got a diverse set instead of like coming up with some measure of diversity for the population. So there was a mixture of that, and once you have that, you end up with a policy that gets a really high score, but is also not too aggressive. And then finally, that means you have this like GT Sophy that stays really close to the other player, but is also fighting for the position. So it's like this was like pretty nail biting. So it like stays really close to the other player and still tries to overtake. Yeah, and then finally we had to select a single policy for the race that we were having in October, and so there was a question of like we have like every few training iterations we used to save the policy, but we had like hundreds of policies like this. So like which one do we end up which one should we use? So one thing we did was, so this is the entire pipeline. I'll go through it quickly. So we used a simple filter for things like, oh, you shouldn't be crashing, or you should like try and find the Pareto front of policies that are completing the time trial in like a certain amount of time, or like the fastest ones that are there, things like that. Then we did an enathlon, which was basically check each policy for all the different skills that we want. So can it like do slipstream passing? Can it like get past the chicane quickly? Things like that. And then we chose a few policies that came out on top in that enathlon. And then we raced all of these policies against each other, found the best couple of policies in these. So that came out of that tournament, smelling of roses. And then finally we had actual humans play against these to then be like, okay, yeah, this policy is the one that we want to use. Yeah.
Does each of the policies tend to use like specific strategy or dominate predominantly specific strategies? Is that the idea?
There are yeah, a bunch of like different like they either use different strategies or they prefer certain skills over others.
They'll still show like a mixture of skills. It's just they'll be dominant in one.
Kind of, yeah. And what happens over here in the PvP is then like you root out ones that can like automatically you get policies that are diverse and can like take advantage of other policies that are maybe not good in certain places.
Do you think like he's talking about certain strategies that were dominant? Do you think like human drivers can like learn from these policies? Like in chess, when you have like, chess players train on.
Yeah, for sure. So there's a mode in GT where you follow like the ghost of another player who has done that same track before, and so you can learn from like where they are at different points in the track. And so for sure, like human players now that we've defeated the best players, are using like learning from Sophy and getting better. Yeah, and then we also like kind of formalized this idea of like how to pick the best policy, and like came up with a better approach for how to test different policies. If you have a limited budget, which are the best policies to test so that you can then find. And this is another sort of like paper that came out of it. Yeah.
You ever seen this work on model merging, like model soups and stuff?
Oh.
They like take different models and then they average them. Like,
I've heard of this. Like, I'm not sure how principled that is. Like.
there's like a bunch of theory on it now.
Oh, okay. I should look
maybe
into
take
it.
a look at
Yeah,
it.
yeah,
It
yeah.
works surprisingly well.
Okay, yeah, I should take a look. Yeah.
So did you have like one policy for each track and each car, or did
Yes.
you have like one?
Yeah, it was one policy per track car pair. We had 3 tracks, 3 cars. Like each, this was one pair. So we had like Seaside with this car, Maggiore. So this is like a regular car that you can find on the road. Maggiore with this like I think Formula 3 or something like that car, and then this is like a Red Bull car that we used at Sarth.
Okay. And then also like,
Yeah.
did you train them all like from scratch, or did you have
Yes.
did you do some transfer learning type thing?
No transfer learning, no human data, just like from scratch. I'm gonna rush through this a little bit because I want to get to like the other bits of like how we got the agent in. So I'll skip this. This is an interesting one to look at. So you have 2 GT Sophys overtaking 2 humans. So this is a Sophy. These 2 are humans. These 2 are Sophy cars. And what they did was like they slowed down before the turn came more than the other humans did, and then ended up overtaking them at the turn. And the other interesting bit is that both of these cars, even though it's the same policy, took different lines. So they're not like they're behaving slightly differently based on like very minor, I think, stochasticity because of like how the actions are going in or some stochasticity in the game. And then the other bit is like the same place where we had like a timid agent earlier, now like have an agent that really goes for it and tries to take the lead. Yeah.
The car is like shaking a little bit. Is that like, you said that like you saw like the driver turns into like a human, but does that like shaking have any detrimental impact or not at all?
Detrimental as in like to the speed and things like that. So it's not having a detrimental impact to the speed, but it's definitely not human-like. So it's like there's a little bit more like shakiness that maybe humans wouldn't do. So yeah, but we didn't explicitly regularize it to be like, oh, like drive like a human. Yeah. So then like the final result in October was that we like GT Sophy won against these like top 4 humans, where before they had lost like 70-86. Instead it was like 52 104 52. Yeah. Okay, now I like shift focus, and like we won against these best humans in the October race. Now there was a lot of interest from the game studio to actually get this agent into the game, but not in a way that like we just beat everyone every time. That's not fun. You want it to be a challenging agent. So what we did was February 2023, we released Sophy on another 4 tracks with certain certain cars as a time limited beta test to like see like do people actually enjoy playing against Sophy, and so it was like 5 car races on 4 tracks. The human would be one of these like 5 cars. So the other 4 cars are Sophy. The first 3 cars are Sophy, and then the last car is Sophy. And then the human always starts with a faster car, so that like Sophy can't always win. And that's the way we sort of like made it equal. And this was like a very successful deployment. We got really good feedback from the community. It was like it's like a lot of like good comments. And a lot of players said that they learned a lot about how to drive differently from Sophy. So so that was really good. And then some of the bits that changed was, instead of a single policy for each car and track and things like that, we have a single policy now that can drive with multiple cars on a single network. This is definitely required because like the studio was like, oh yeah, we can't like send a bunch of policies onto the PlayStation. Just like pick one policy and give it to us. and the focus was on making the game fun over there. So there's a lot of like interaction with the game designers to like pick the policy and things like that. Yeah, and then a lot of like little things, a lot more like human in the loop when trying to figure out which policy you want to use. With this successful like beta test, like the studio was convinced now like, okay, we can get Sophy into the game. So like November of last year, they released GT Sophy 2.0, which was actually like a permanent release. It's in the game permanently now. And this is a trailer for GT Sophy. While the trailer is going on, I'll just talk a little bit about like now we at that November release we had like 340 cars that can be controlled with a single policy with 9 different like tire compounds and 9 different tracks. And players are allowed to choose like whether they want to play with Sophy or like the regular AI. So this like we don't force this on them. And players can also choose like any car they want, and then Sophy like chooses cars to sort of like be close to that in order for it to be fun. Yeah, I'll skip this as well. It's basically like Sophy driving really well and players having fun.
In the background, when this
so
AI gets it right,
the ones that have the emoticons are all Sophy cars.
Move off of its line, it will follow your slipstream, it will do everything.
This was not something we trained them for the emoticons.
Challenge possible. And that's where I said
yeah, again like bunch of good feedback. And it's like it's now a permanent part of the game. You can like if you have a PlayStation, if you have GT, you can go and play against Sophy. Though now we have more cars and more tracks that I'll talk about in a bit. There's let's see. So we modified the features and bits like that as well. So we gave more information to Sophy now that it needs to use more cars. So it has to understand what car it's driving, and instead of just giving like an indicator, we give it like important features like how big the car is, what the mass of the car is, and things like that. And you can play against like up to 19 other cars instead of just like 4 like earlier. And yeah, the other thing is like we also adjusted some of the rewards so that the agent is now more timid, so that we wanted the agent to not be like on the edge as much. So there was some update of like the reward function as well. Yeah, and then finally this like last July we've added a bunch of more tracks, including this one called Nürburgring, which is called I think like the Green Hell or something. Yeah, Green Hell. And now it's like more than 400 cars that you can play with. So basically like we're ramping up, we're trying to like basically make it so that we replace the in-game AI with an RL trained agent and slowly handing over control to the studio so that they can do all of this. To end with, some of the things that we are looking at is also like right now we don't take into account like tire wear and like you're running out of gas and things like that. So there's some of those strategic decision making is coming in. And then the last bit we want to try is like driving with style. So this is an agent that was trained to maximize drifting. And then as RL agents do, it did like, it started reward hacking. So when we asked it to drift, it realized what we want is like more tire slip. And so it does a really cool trick at this next turn. So it decided, okay, yeah, this is the right way to drift. So you want style, but maybe not that much. And then we're also trying to look at how much all these like things that we've come up with are applicable to other games at Sony. Yeah, so I think that was it. I kind of rushed at the end, but I think we're on time.